All right. So this is cis256, and today we will talk about new chapter, and this is about graphs. Everything about graphs. Okay, so in this week, we will briefly introduce what a graph is in computer science, and we will use multiple representations to implement a graph, ADT, and we also will talk about the two very important way to traverse a graph, aka DFS, depth first search, and BFS, breadth first search. So what is a graph? Well, in a lot of real world examples, you can see in the left side, there is a maze, and the problem is how to find a route from the entrance to the exit. And the other application on the right, you can see a map from Yale to Harvard, and you have a starting point and end point. How are you gonna plan a route from A to B in the shortest path or in the fastest way? So these are, two examples that where graph algorithms are really helpful. So we'll talk about this application later. And then there's another example where you have so if you are in a computer science department and there's a bunch of courses, and of course, there's some prerequisites for each course. Like, for example, CS220 has two prerequisites, Math 151, CS 150. So given the prerequisite of each course represented by a node in the graph, how you will compute a order where if you take that course in order, you will complete all the curriculum in the, for example, CS department, right? So this is one of the classical problems where you can solve it by, many different ways, but one of the graph traversal algorithms that will help you to do topological sort if this graph is actually a directed as a acyclic graph. So we'll talk about all these details. So let's get the vocabulary out of the way. So what is a vertex in a graph? The graph is a collection of vertices and edges. The vertex is also called node. This is a fundamental part of graph, right? We can have a name for each node. We can call it the key for the node, and you can have additional information for vertices as you can treat it as object-oriented way. And the additional information can be the payload to that key, all right, to that vertex. Okay, so that's vertex. It's an object that at least have a name or a key and then maybe some payload. Edge is also, you can see the like arc, in this case, it's just the arrow in the graph. So edge connects two vertices together, right? They show some kind of relationship. And you can see edges can be one way, like only from one node to another, or two ways. It can be two directions, both directions. So if it's one way, we call it a directed graph or a digraph. And if it's two ways, that's undirected graph. Okay. So the class representation is direct graph because there's dependencies for prerequisites for the class. And finally, a graph may have a weight. The weight is basically like in the map. Example, from A to B, there's two different routes and represented by two different edges, but each edge may have a weight on it. That means how far it is, right? So it's weighted by the weight or distance, etc. Edges can be weighted, so that's cost to go from A to B. So in that map example, the edge may represent distance between the cities. Okay, so here's some formal definition of a graph. So the graph is actually a collection of vertices and edges. V is a set of vertices, and E is a set of edges. Each edge is a tuple, where the V and W are or belong to vertices set. We can also add weight to the H tuple to represent the weight. And a subgraph is basically a subset of graph nodes and edges, right? Okay, so this figure number 2, shows another example of a directed graph, because the arrow represents the direction from one node to another, right? Then we can represent this graph as set of 6 vertices and 9 edges. Okay, so that's a definition of graph. Okay, so what is path to the graph? Well, a path in a graph is a sequence of vertices connected by edges, right? It's like a mapping, you go to city A to city B, and with some couple of nodes in the middle. Okay. So the paths can be weighted and non-weighted, and so weighted means each path has a cost with it, right? And the weighted path length is the summation of all the weights along the edges in the path. And if it's unweighted, then each weight is going to be 1, right? So you just count the number of edges connecting A to B. That's the number, the length of the path, right? So that's how to define the path length. Okay, so cycle. So what's the concept of cycle? So in a direct graph, okay, if there's a path and starts and at the same vertices, that means we encountered a cycle. So in other words, if you have a tree or graph, so obviously tree has a cycle. No, tree don't have a cycle. You can start with the root, and you cannot go back to the root. So that's a different. So tree is a example of a acyclic graph, no cycle in it. Acyclic. A means no cycle, and so yeah, that's one definition. No cycle is called acyclic graph, and a directed graph with no cycle that's called a directed acyclic graph or DAG. So the previous example where we show this course dependencies, this is typically a acyclic DAG, right? Okay, so that's some nomenclatures. So how to implement a graph, abstract data set type. A graph is a class, has several methods, right? We can add vertices to the graph. We add edges. Edges contain at least 2 components from and to. Okay, and you may have a weight, right? So there's another example of add edge with 3 parameters. We can get vertices. We can get all the vertices of the graph, right? We can get one vertex given the key. And there is a in operator to return if the vertex is in the graph or false otherwise. All right, so now let's talk about how to represent a graph in program. So there's a couple of different ways. One way is to use what we call adjacency matrix. So here in the matrix, in 2D matrix, rows, so each node is a row, you arrange them in a row and column. And so obviously, so for each node to any other node except themselves, if there is a number in it, that means they're connected. If there's no number in it, that means they are not connected. And the number itself can be a weight, right? So this matrix shows that V0 and V1 is connected with weight of 5. V0 and V5 is connected with a weight of 2. V0, V4 is connected with a weight of 1, and V5 and V4 connect with a weight of 8. So that's what we call adjacency matrix. So what's the pro and cons for using adjacency matrix represented? Well, if there's a lot of connections, then you use that is very convenient because you can immediately tell if the each two nodes are connected or not. And if given V1, I can also quickly tell how many nodes are connected to V1 by looking at just that row, right? Iterate that row and see if they are connected. Okay. So obviously, if there's not many connections, we call the sparse matrix. Then you waste a lot of space, and there's a lot. You have a sparse matrix. That means you have matrix with a lot of empty cell. That's a waste of space. So is there a better way? Okay, so there's another way which we call adjacency list. So what is adjacency list? So basically for each node of vertices, we keep a list of adjacency node that is adjacency to that node, right? So given that it can immediately, usually we can represent as a map, okay, or a dictionary in Python. We can use vertex as a key, and the value is basically a set or a dictionary of so it's a list of dictionaries with key is vertices ID and value is its weight. Well, actually, yeah, a list of key value pair. Okay. The value is weight. Okay. So that's adjacency list. Okay, so here is a implementation of the vertice class. You can see this class has a key that's mandatory, but and then also has a list of a dictionary of adjacency list, right? Adjacency vertices. So if you want to add its neighbor with default weight 0, you can just add this to the dictionary with that neighbor as the key. And the value is the weight. Okay. And if you want to get connections, you can just list all the keys that is connected to that represents adjacency nodes. Of course, these are the getter functions for its own ID and weight, if there's anything other than 1. Okay, so weight is the value of the dictionary. So that's how vertices is implementing Python. It's one way. You can actually obviously implement another way. So the graph is a collection of edges and vertices. So the vertice list is another dictionary, and the number of vertices is kept as a separate property here. If you want to add vertices here, you just give them a key, and so increment the number of vertices by 1, and you create a new vertex object with a key, and you add that to that vertice list dictionary. So again, there's two keys here, redundant, but the new vertex is created in the adjacency list. So this is still a implementation. And then finally, you can get all the vertices with that node. If the node, you can return the vertices list and is the key in that dictionary. Of course, if it's not there, then you return none. And it contains, which basically simply you can see if the key is in that vertices list key. Also, you can add edges to the graph, not only the node, but the edges, because you may have two nodes that's not connected. If they're connected, like F and T. So if any of them are not in the vertex, you add them. And after that, you can add the neighbors. Basically, the T neighbor, sorry, F's neighbor is T. Right, so this is one way. If you two ways, then you have to add T's neighbor is F. Okay, this is directed and there's undirected, then you have to add twice. and you can get vertices by keys, and values is the the weight. All right, so that's the graph implementation in Python. So keep that in mind. Now let's talk about how to traverse a graph. So adjacency list, adjacency matrix are two common way to represent a graph. But in computer science, in our purposes here, most of the graphs are sparse, so use adjacent list has advantages. All right, how to traverse a graph? Well, this is obviously similar. It's like a tree. So tree is a subset of graph, right? And so we know using tree, we can use BFS and DFS too. BFS just means you go to level by level. You go to the root, and then you go to next level before you go to next level. Is that clear? So basically, to do that, each level is like you can push each level into a stack, and until you go to the bottom, and you pop them off and to deal with it. Right? So, oh wait a second. Sorry, it's a queue. You put it's a BFS. You put in the queue. So queue means first in, first serve, right? So first in, first out. So yeah, you want to serve the root first, and before you go to next level, right? So each level you get pushed to a queue and be processed in order it was received. That maintains a breadth first search. So you want to visit level k away from the source vertex before you visit k plus 1 edges away until no more vertices reach from S. So here is the order 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what's the runtime complexity? Well, you have to visit each vertices and edges at least once, so it's O of V plus E. And all the edges could be between O1 and OV square. Think about it, right? Because if any two pair of vertices are connected, then it's V squared number of edges. Okay, so here is a sample implementation of BFS. In Python collections module, you have a DEC, double-ended queue. We use that to key data structure to queue the nodes, right? So to traverse the graph, which is a dictionary, and given the source, you start with the source. You put the source into the queue first, and while there's empty, the queue is not empty, hence the length is greater than 0. You pop left. Pop left basically say I'm gonna get the first nodes from the queue, which is source. You print that, and for any neighbor in the current nodes, you append that to the queue. Now after that, it will be pop left in the order is received. So by using a queue or DEC, this is how the BFS is done. Okay, the queue is here to maintain order. Okay, another way is depth first search, where you go to one branch all the way to the bottom before you go to other branch. Okay. This is often used in the maze exploration, right? The BFS is often used in the map, find the shortest distance, and this DFS, depth first, is often used to find a route to the maze. So, and of course, the complexity is the same as BFS. And also this graph is represented as adjacency list. Okay, so here is another implementation of DFS, similar to BFS. This time we're gonna use the stack, because the stack is first in, last out, because you want to deal with the latest item on the stack first before you go back to the root, right? So in this case, we're going to use the stack. And then we also keep a set of visited nodes. You'll see why in a moment. So the stack initially has a root in it. And of course, while the stack is not empty, we pop one from the stack, right? If the vertices that's popped from the stack is not visited, well, we can add to the visited set because we are visiting it. And we can also put all the neighbors of that vertices, graph vertices is a dictionary of sets. And minus visited is the one is already visited, right? So if any nodes vertices in that graph, its neighbor is already visited, it's a JSON list, then we just subtract. We don't need to put it into the stack because it's already in the stack somewhere or popped off already. So that's just a set operation to subtract what is visited and then return visited. All right, and that's the iterative. Now, but oftentimes we don't use the stack. Why? Because a function stack is naturally a stack that we can use. So oftentimes we implement this as a recursive function. So how it does is, this is a more typical way of doing DFS using recursion, graph, start, and visited. So visited is a set to begin with, and you add a start. And for all the neighbors, one by one, from the starting neighbor, the neighbor of the start point in graph, if that is not visited, then we're gonna do this graph search recursive call again with that point. Okay, so we're dealing with the next point before we're dealing with the parent, and then here will be added to visited in this step, right? And then return visited. So basically, you're using the function stack as a real stack to push that to, and then you are dealing with the last one because if there is the leaf node, then it's going to be deal with first. So that's adjacent list. Okay, let's use some examples to illustrate how BFS and DFS works. So let's do a example code, see if you understand this. So the sample code is as follows. We're gonna choose DFS.py. Okay, so the question is like this. Write a function, undirected graph or path, takes an array of edges from undirected graph in the two nodes, A and B. It should return a Boolean indicating whether or not there exists a path between A and B. So given the graph, there's a path between A and B. You can do it in either BFS and DFS, right? Nonetheless, we're gonna do is, first of all, build the graph first. Okay, build the graph first. So given edges, which is a list, and return a dictionary, which is the graph, represent the graph. And of course, we're gonna import from collections module, import default dictionary, and okay. So now we're gonna convert edge list. So what's the input here? Okay, let's do some notes here. This function, we're gonna convert. All right, we're gonna convert this edge list, right? I to j, k to j. So you're given the list of lists as a adjacency list, right? No, you're given the edge list, which is A and B, C and D are connected. It's not adjacent list. Adjacent list is like a node and what's the neighbor. So you want to convert to adjacent list for undirect graph. That's the first step. How to do that? Well, let's see. So first of all, my graph, we can represent as a default dictionary of list, right? It's default list. And so I'm looking at for each edge in edges list, what do we do? Well, we unpacked edge 0 and edge 1. So there's 2 nodes in each edges A and B. So graph A, so with A as a key, I'm going to append, it's a list, right? It's a list, append B to list. Now, of course, it's a undirected, so we're going to do again, graph B, append A. So this way you connected A to B and B to A. So for each edge you do that, then the adjacency list is done. And we're going to simply return the graph. All right, so that's how you're going to build a graph. Now with that, so we're going to implement the main function which is called undirected paths. So if this exists, we get in the edges, which is the list of list, right? And we have node A, which is a starting point, which is string, and node B is also string, starting point, and then endpoint, sorry. And then getting Boolean if the path exists or not. True exists, not. So we're gonna define it as a DFS recursive function call. We have adjacency list, we have source, we have a destination, and we have a visited set to indicate that the node is visited or not. So here is a base condition. If source is equal to destination, that means we reach the destination, right? Then we return true. Hey, congratulations. Now, if not, so for each node in the adjacency list of the source, right? Source, if node is not in visited, okay? If it's not in visited, then we're gonna add this to the visited set, okay? This is to avoid cycles in the graph, okay? Otherwise, we're gonna maybe have a cycle in the graph. And also, we're gonna do recursively with node, for each node in the visited, and go to destination node B and call that again, right? If anytime we return a true value, we're gonna return true, okay? Now, somebody may ask, why can't I just return this function? Because this may return false, right? But we don't want to return false prematurely, because just because one branch is false doesn't mean the whole branch is finished yet. So we only return false when we exhausted every single branches, okay? So you will see why. So after this for, if nothing get returned true, then we must have exhausted all the possibilities, okay? Then you can return false, okay? So this is important, okay? So some comment, only when at this stage, you have exhausted all routes and cannot find a path between node A and node B. Then you return false, right? Okay, so this is definition. First of all, we're going to build adjacent list using this build graph function. And then we're going to say visited is initially a set, and then put node A itself to the set first. And I'm going to return DFS. We're going to go adjacent list, node A first, node B second, and visited along with it. Okie dokie. we have finished this problem. Okay. So this is the example here, and example directed graph, and then this is a connected components example. So what is a connected components? Well, so if you're given an adjacency list of undirected graph, right, it should return number of connect components within the graph. You already given a adjacency list, so you don't need to convert it to one. So for example, here, it's kind of hard to imagine, but you want to draw them up. You have a couple nodes from 0, 1, 2, 3, 4, 5, and 8, and each one has a connected or unconnected adjacent list. And given that picture, can you tell me how many components are connected and how many are not? Okay, so let's see. Yes, can I draw it? Well, I guess it's better to have a visualization. Yeah, visualization. I don't know if I can maybe draw it. Let's see. Okay, I can have an annotation. Hold on a second. Okay, here. Draw. All right. So we have 0 is connect to 1 to 0, connect to 1, right? And 1 connect to 0, and there is a 5, and then there is a 8. Right, 0 connect to 1, 5, and 8. 1 is connect to 0, 5 is connect to 0 and 8. 8 is 0, 5, 2 is 3, 4, 2, 3, and 4. And 3 is 2, 4. 3 is 2 and 4. And 4 is 3, 2. So you can see these 3 are in a lonely island, right? Connected components. And these 4 are in lonely island. So there's 2 islands. And the answer is 2. Okay, so this is how we do a connect component. So how to count? Well, in the graph theory, you can start as any node, like node 0. And you do DF search until you cannot reach anything else, right? You do DF exhaustive search, DFS, until you're going back. That means you are exhausted. And then you start with different nodes so along with that, you mark each one visited. So next time you're not visiting, these 3 are not visited, then you just pick one and do the DFS again, and you covered all of them. And once you repeat those algorithms, and you can count how many lonely island or connect component are there. Okay, so that's the idea. Translate to code is basically that, right? So basically, you have 2. So basically, you have a recursive function, DFS again, called explore, where you get a adjacency matrix, adjacency list, a source and visited. And so if the source isn't visited, then you return the false because you already visited that, so you don't need to explore anymore. And otherwise, you add to visited, And for each neighbor in the adjacent, this is a familiar formula, right? This is where adjacent list is shine because you can easily say, my neighbors, easily collect neighbors. And you can explore them each one by one until you finish it. And you can return true, explore the component as far as possible. And then whenever you return from this, you counted one island and you just add one, can't start by 0. And then you just do that again for each other node. Now, don't worry if there's nodes already visited, you can just immediately returns. So by this for loop, you are counting number of island, right? Every time you return from the explorer, you have exhausted a island using DFS, and finally you can return the count. So that's how you use DFS to calculate number of a lonely island or connected components. Okay, so in this lecture, we talk about graph definitions, acyclic and cyclic graphs, cycles and such. And we also made an example of how to organize a graph in different format, adjacency matrix, adjacency list, and I have a couple examples for the BFS and DFS search. Next lecture, we're going to talk about more applications. Stay tuned. Okay, bye.